All right, ready to dive into something pretty mind-blowing.
I'm all ears.
Nuclear fusion.
Ooh. Now that's a big one.
How we're always on the hunt for those clean energy solutions.
Right.
Well, this just might be the holy grail.
It's like the ultimate energy source, isn't it?
Yeah, it is.
I mean, it's what powers the sun.
Literally harnessing the energy of the stars. Sounds like something straight out of science fiction.
You would think, but it's real science.
So we're talking real science happening right now.
It is, and that's why we're here today, to unpack just what fusion is, why it's such a game changer, and of course the challenges scientists are working on to make it,
to make it a reality.
A reality, exactly.
Okay, so way back in school, I remember learning about atoms. How does fusion actually work at that level?
All right, so think of it this way. Fusion is kind of like taking these tiny hydrogen atoms and merging them together to create a heavier atom.
Okay.
And in that process, a huge amount of energy gets released.
So instead of splitting atoms like in nuclear fission, we're combining them.
Exactly. We're basically doing the opposite. And get this, the fuel we're talking about, it's readily available.
Wow.
Deuterium, which we can get from seawater.
Okay.
And tritium, which comes from lithium, a virtually limitless supply.
So no more worries about those dwindling fossil fuels or the environmental impact.
Exactly. Fusion doesn't produce any greenhouse gases. It's clean energy.
Wow.
On a whole other level.
What about that radioactive waste that comes with nuclear fission? Is that a concern with fusion too?
That's one of the amazing things about fusion. It produces very minimal radioactive waste, and what it does produce is short-lived, so you wouldn't have to worry about those long-term storage issues that we have with current nuclear power.
So it's clean, it's got a virtually limitless fuel supply.
Yeah.
It almost sounds too good to be true.
Yeah.
What's the catch? What are the challenges that are preventing us from having fusion power plants everywhere?
Well, the biggest hurdle, honestly, is containing the reaction itself. So imagine trying to hold something multiple times hotter than the sun's core.
I can't even fathom that kind of heat.
That's what we're dealing with.
Wow. What makes it so difficult to contain?
Well, it takes a tremendous amount of energy just to get the reaction going. And the materials that we use inside the reactor, they take quite a beating from these extreme temperatures.
So it's not as simple as just building a super strong container.
No, it's not. Scientists are working on incredibly sophisticated methods to contain this superheated matter. It's called plasma.
Plasma? Is that like a gas?
It's similar to gas, but it's so hot that the atoms have been stripped of their electrons. It creates this kind of electrically charged soup that we need to control.
So they're essentially trying to build a cage for a miniature sun in the form of this plasma.
That's actually a pretty good analogy.
Okay.
But even building the cage is incredibly complex. Some scientists are using these powerful magnets to contain the plasma, while others are using these intensely focused lasers. It's cutting-edge science.
It sounds like an incredible challenge. Are we seeing any progress? Any reason to be hopeful?
Absolutely. There have been some incredible breakthroughs recently.
What has you so optimistic?
Well, there are two main approaches to achieving fusion here on Earth: magnetic confinement and inertial confinement.
Okay.
And both are seeing some pretty significant progress.
Okay, break those down for me. What are the key differences between those two approaches?
So magnetic confinement fusion uses incredibly powerful magnets to create this sort of invisible bottle that holds the superheated plasma in place. The most common type of magnetic confinement device is called a tokamak.
Oh, yeah.
Which is shaped like a donut.
I think I vaguely remember hearing about tokamaks. Can you paint me a picture of how those work?
Sure. So imagine a giant donut-shaped chamber wrapped with these powerful magnets. These magnets create a magnetic field that acts like an invisible force field, preventing the plasma from touching the walls of the reactor. And remember, we're talking about temperatures hotter than the sun's core. So keeping that plasma contained is absolutely crucial.
So it's like suspending that miniature sun in midair using magnets.
Exactly. It's pretty amazing that we can even do that.
That could even do that, yeah.
It really is. It's a testament to human ingenuity, but of course there are challenges. Keeping the plasma stable inside a tokamak is incredibly difficult. And any disruptions can actually damage the reactor. So it's this constant balancing act, trying to maintain those extreme conditions without letting things get out of control.
So what about the other one?
Right, inertial confinement fusion. So instead of a steady, continuous reaction like in magnetic confinement,
Hmm.
inertial confinement aims for a rapid-fire sequence of tiny fusion explosions.
So more of a pulsed approach.
Yes, exactly. So imagine a tiny pellet of fusion fuel, smaller than the tip of your pen.
Wow.
And we use these incredibly powerful lasers
Okay.
to blast this pellet from all sides simultaneously,
Hmm.
compressing and heating it
Okay.
until it implodes, and that implosion triggers fusion.
So it's like creating a miniature star
Yeah.
for just a fraction of a second, over and over again.
You got it. That's a great way to put it. Remember the National Ignition Facility, NIF?
Yeah.
They've actually achieved ignition using this inertial confinement method,
Right.
meaning that they produced more energy from the fusion reaction than the laser energy they used to start it.
I remember that. That was big news. It really felt like a major milestone.
It was, absolutely. But just like magnetic confinement, inertial confinement has its own set of challenges as well.
Right.
For one, it requires extremely precise and powerful lasers to achieve that perfect implosion.
Right. I can imagine that that's not easy to do.
It's not, and those repeated explosions put a lot of stress on the reactor itself.
Right. So both approaches have their hurdles, but it sounds like there's real progress being made on both fronts.
Yeah.
It's fascinating that we have these two completely different approaches to achieving the same goal.
It really is. It highlights the creativity and ingenuity of the scientists working in this field. And what's even more exciting is that it's not an either situation.
Right.
We could very well see a future where both magnetic and inertial confinement play a role in our energy grid.
So maybe we'll have a mix of tokamaks
Right.
and these laser-powered reactors, each with their own strengths and applications.
That's it. And that brings us to another really encouraging aspect of fusion research. The increasing collaboration that we're seeing between governments, research institutions, and private companies.
It does feel like there's this real global effort building momentum. What's driving this collaboration?
Well, you have these massive international projects like ITER,
Right.
which is a collaboration between 35 countries,
Wow.
all working on magnetic confinement fusion. At the same time, you have all these agile startups emerging, developing these innovative reactor designs and laser technologies for inertial confinement.
So it's like a fusion ecosystem where everyone is learning from each other and pushing the boundaries of what's possible.
Precisely. And this collaborative spirit is really accelerating the pace of innovation. Many experts now believe that we could see commercial fusion power much sooner than we initially thought, perhaps even within our lifetimes.
That's exciting to hear. Let's shift gears for a moment. Let's talk about what a fusion-powered world would actually look like. We've talked about the science and the challenges, but what would this mean for our lives?
For the planet, it's hard to even imagine what that world would even look like. It feels like we're talking about a complete paradigm shift.
Yeah, it really is. I mean, think about it. Energy scarcity would
Right.
become a thing of the past. Developing countries would have access to the same clean and abundant power as developed nations. It could really level the playing field in ways we haven't even considered. No more reliance on those fossil fuels.
Right.
No more concerns about carbon emissions and their impact on the climate. It almost sounds utopian.
It's definitely a promising future.
Right.
And the implications, I think, go far beyond just energy production.
Okay.
Fusion could revolutionize entire industries, like transportation, manufacturing, even space exploration.
Okay, now you're getting me really excited. Give me some concrete examples. How would fusion transform these industries?
Well, imagine desalination plants powered by fusion,
Right.
providing clean drinking water to regions struggling with drought. Or think about spacecraft,
Right.
propelled by fusion engines, allowing us to travel to distant planets in a fraction of the time it takes now. I mean, the possibilities are mind-boggling.
It really is incredible to think that fusion could hold the key to solving some of humanity's biggest challenges. But with any powerful technology, there are always potential downsides, right?
Yeah, of course.
What are some of the risks that we need to be thinking about as fusion gets closer to becoming a reality?
You're absolutely right. We can't just focus on the positive. One concern is the potential for weaponization.
Okay.
I mean, fusion reactions release these enormous amounts of energy, and that could be harnessed for destructive purposes.
So it's the classic double-edged sword. Technology that offers incredible benefits, but also carries the risk of being misused.
Right. And that's why it's so important to have strong international agreements and regulations in place to make sure that this technology is developed and used responsibly. We need to prevent it from becoming another source of conflict or instability in the world.
It would be a real tragedy if we solve the energy crisis only to create a new set of global threats. Are there any other potential downsides we should be considering?
I think another really important one is ensuring equitable access to this technology. We need to make sure that the benefits of fusion are shared fairly, both within and between countries. We don't want to exacerbate existing inequalities or create new ones.
It's a good reminder that technological progress doesn't automatically translate into social progress.
No, it doesn't.
We need to be mindful of those ethical implications of fusion and ensure that it's used to create a more just and sustainable world for everyone.
100%, yeah. The development of fusion energy is a human endeavor, and its success hinges on our ability to navigate these complex challenges responsibly and ethically.
It's a daunting task, but also incredibly inspiring. I mean, we're talking about nothing less than shaping the future of humanity.
That's why it's so important for everyone to be informed and engaged in this conversation, not just scientists and policymakers. The future of fusion energy is ultimately in our hands.
So as we wrap up our deep dive into nuclear fusion, what's the key takeaway you want our listeners to ponder?
For me, it's the power of human ingenuity and collaboration. Fusion energy was once considered a distant dream,
Right.
but thanks to the dedication and perseverance of scientists and engineers around the world, it's now within reach. It's a testament to what we can achieve when we work together towards a common goal.
And for me, it's the importance of thinking critically and ethically about the technologies that we develop. Fusion has the potential to really transform our world for the better, but we need to be mindful of the risks and make conscious choices to ensure that it's used for the benefit of all humankind.
Well said. It's been a fascinating exploration, and I hope our listeners have come away with a deeper understanding of this incredible technology and the possibilities it holds.
And maybe even a little bit of that starry-eyed wonder that comes with imagining a future powered by the stars. Until next time, keep exploring, keep questioning, and keep dreaming big.